Hello everyone. So today we will discuss a problem from real analysis. Okay. So I have written the problem on the screen and I read the question and we will solve the question in detail. Okay. Yeah. So first what the question says, if if from closed interval AB to R be a non-negative continuous function on AB. Okay. So we everybody know what we mean by continuity on a set. Continuity on a set means it is continuous at each and every point on that set. Okay. So here we have given that f is a non-negative, means it takes the values between it takes the values non-negative values, means greater than equal to value. Okay, it does not take any negative value. That's why it takes only non-negative value. Either it can take 0 or it can take positive value. Okay. Now consider a sequence. Consider a sequence n. Sequence is constructed by the help of f. Okay, with the help of f. Okay, the sequence is given that a to b f of x to the power n dx whole to the power 1 by n. Okay. The question is determine whether or not n is convergent. So our question is n is convergent or not. If n convergent, then compute its limit. Okay. There are two questions. So is the question is clear? Okay. So what we have given? We have given a continuous function which is non-negative. Okay. On the interval, closed interval AB. And with the help of this continuous function, non-negative continuous function, we are construct a sequence. Okay, the sequence is given by integral. Okay, so determine whether or not an is convergent. Okay, so we have to determine whether n is convergent or not. If it is convergent, find its limit. Okay, so we are proceeding to the solution. Okay, so solution. Okay. So first of all, we have to ask a question. Okay, whether this type of sequence exists or not. This type of sequence exists or not. If the existence of sequence means I am going to say that this integral exists or not. Okay, first question. So this integral exists. Why? Because f is a continuous function over the interval closed interval AB. Okay, so every continuous function over the closed interval AB is Riemann integrable. So Riemann integrable, f of x is Riemann integrable, and it is non-negative, so it's product f of x square, f of x whole cube, f of x whole to the power 4 is Riemann integral. So this integral exists, and this integral exists, and this integral is positive, so its nth root is positive. Okay, that's the question. Okay, nth. Okay, nth root is it. And so these sequences exist. Sequence exists. So the question about existence of the sequence is clear. Okay. Now we're interested in whether n is convergent or not. Okay. Now what do you need? What do we know about a function which is continuous over the closed interval AB? Okay. So since right since closed interval AB is compact. Okay. Since closed interval AB is compact and continuous and continuous image of a compact set is compact in R. Okay, since domain, codomain, all are subsets of R, so compact sets in R by Hein-Borel theorem is closed and bounded if and only in case. Okay, and continuous image of compact set is compact in R. Because the domain codomain sense, we are not bothering with which topology, which matrix, nothing. Here, all things are usual topology, usual metric. Okay, yeah. So AB is compact, continuous image of compact set is compact in R. So here, compact in R by Hein-Borel property, by Hein-Borel theorem, it is closed and bounded in R. Okay, okay, bounded in R. And by completeness axiom of R, or by completeness, yeah, by completeness axiom of R, we can say that every non-empty bounded set in R has supremum or infimum and infimum. Okay, we know everyone that. Okay, so we will use that. So by completeness axiom of R, so the image of F, image of F is has supremum and infimum in R. Okay, in R. Okay. So by completeness property, so we know that by completeness axiom, this is by completeness axiom of R. Axiom of R. Okay. So every non-empty bounded subset of R has infimum and supremum. Okay. Is it clear till now? Till now, everything clear, right? So from that, so so since its supremum exists, since you present let M be the supremum of modulus of f of x belongs to close interval a comma b. Okay, yeah, it is, and it is exist. This supremum exists. Why exist? Because of the above discussion. The continuous image of complexity is compact in our Hein-Borel theorem. If and only if it is if and only if in R. Okay, in R. In R it is closed bounded, means it is compact, and by completeness axiom of R, image of F has supremum or infimum in R. Okay, so by the above discussion, this is exist. Okay, now from M, now look at M. What we have given information about F. Given information about F, say F is non-negative, non-negative. Okay, that means f of x is greater than equal to 0 for all x belongs to closed interval AB, right? Is it clear? So f of x is non-negative for each point. F of x is non-negative function on closed interval AB. Okay. So f of x is greater than equal to 0. So from that we can say that modulus of f of x is nothing but f of x itself. Okay. It is clear, right? Now, since f is non-negative and m is the supremum value, then m is also non-negative. Okay, m is also non-negative. So we have to find some sequence limit, right? We are not bothering about that sequence till now. So we are just use the hypothesis uh, side by side and term by term. Okay. Is the hypothesis. Now, m is greater than equal to 0. So there are two possibilities, right? There are two possibilities. Either m equal to 0 or m is positive. There are two cases. So we are considering the first case. What is the first case? Case number 1. When m is 0. M is 0 means supremum of modulus of f of x belongs to AB is 0. That means modulus of f of x is less than equal to 0. for every x belongs to close interval a comma b, right? For every comma b. So let me write it clearly. Let me write it. That is f of x, and that is holds for every x. Okay. So since f is non-negative already given, so a 0 less than equal to f of x less than equal to 0 for every x belongs to ab, right? For every x belongs to ab. So from that it is clear that f of x is equal to 0 for every x belongs to ab. So now for every f of x is 0, then n, the sequence n in this case is identically 0, right? N sequence is null, n sequence, each term is 0 for n sequence. For each n belongs to natural line. Okay. If you know the construction of n sequence, then it is clear, right? It is n is nothing but integration a to b f of x. Since f of x is 0 here, so the each term of the sequence is 0. Okay. Now n is 0. So n converges to 0. N converges to 0 as n tends to infinity. And 0 is the supremum. That is the m. Okay. That is the m. So in this case, n is convergent and its limit is the supremum of f of x. But since it is a non-negative function, so we don't need to take the modulus here. Okay, clear? Yeah. Now the question is what what will happen for m greater than 0? So case 2 when m greater than 0. Okay. So what will happen for the case when m greater than 0? Okay. Since m greater than 0 and m is the supremum of f of x. Okay. Since f is non-negative, so we don't need to consider the modulus. Again and again, I am saying, okay. Since m is the supremum, if we subtract something below that, okay, some positive value if we take below that, then there exists some element of that functional value, that function, okay, by property of least upper bound, because it is a least upper bound. So if we take something, if we subtract something positive value from that, that will not be an upper bound. So there exists some element of the set outside that value. Okay. So what do you mean by that? Choose epsilon positive such that 0 less than epsilon less than m. Okay. Choose epsilon positive. Okay. Then there exists x naught belongs to close interval a comma b, such that m minus epsilon greater than less than f of x. Okay. M minus epsilon less than f of x. Okay, clear? Yeah. Now, now, uh, hmm. Now just use something called, uh, do you know something called neighborhood property for continuous function? Yeah. So we'll use the neighborhood since, and this is positive. Okay. Since f of x naught is greater than m minus epsilon, f is continuous, m minus epsilon, this is also continuous because it's constant, fixed constant. So there exists a neighborhood of x naught. Name it that neighborhood is c comma d. So that by neighborhood property of of continuous function, there exists a neighborhood, there exists C, comma D containing x naught and C comma D contained in A comma B. Okay. C comma D is contained in A comma B. It contains X naught and C comma D is internally such that f of X greater than M minus epsilon for every X belongs to C comma D. Okay. This is the neighborhood property by neighborhood property. Okay. Why do consider that? Because we have to something to show about N. Okay. N is convergent or not. Okay. So for M greater M equal to 0, the case is clear. For M positive, we have to use the properties of continuous function. Okay. Now consider that. And f of x is less than equal to M. Because M is the supremum over closed interval A comma B, and if we take the whole supremum over closed interval A comma B, and we are taking the subinterval closed interval C comma D. So the supremum value over closed interval C comma D is less than or equal to supremum value of closed interval A comma B. Okay, because closed interval C comma D is subinterval closed interval A. Okay. Now I'm just rewriting this that m minus epsilon less than not equal, less than yeah, m minus epsilon less than f of x less than equal to m for all x belongs to C curve. Okay. Now, here we take that uh, we have to form the sequence n. Okay. The m minus epsilon to the power n is less than f of x to the power n. Okay. And that is less than equal to, we are not considering that term. Okay. Now, till. Okay, we are not considering that term for as of now. Okay, we will work on that. Okay, this is f of x. Okay. Now, m minus epsilon to the power n uh, integration c comma d dx is less than, because the continuity because of continuity, if you know the Riemann integral sum property related to continuity, then take if it both are non-negative function, because this is also non-negative function, this is also non-negative function, that their value differ at least 1 point, so their integral also mm, uh, differ in the same sign. Okay, the same sign means is less than or equal or greater than. Okay, now this is CD f of x to the power n dx. Okay, and this integral is less than or equal to integral a to b f of x to the power n dx. So this is the standard property of Riemann integration. Okay, and this is less than equal to, since f of x is bounded by m all over the interval ab, so this is m to the power n integration dx a to b. Okay, there are so many integration. Now just compute the integration, that is m minus epsilon to the power n, that is d minus c, and this is positive, and less than c to d f of x to the power n dx. This is less than equal to, this is a to b f of x to the power n dx. This is less than equal to m to the power n b minus a. Okay, clear? Yeah, b minus a. Now we are taking the 1 by n, because in the sequence of construction of n, if we look closely, we will see that a to b f of x to the power n dx and whole to the power 1 by n is there. So if we are taking 1 by n, means nth root of everywhere. Okay, so nth root of everywhere, because it is total is positive, so we can take the nth root trivially. Okay, now that is m minus epsilon, which is d minus c to the power 1 by n, and less than equal to, we are just ignoring that part because we are considering this part only. So this is less than less than this will be an is less than equal to m b minus a to the power 1 by n. Okay. Now we are in the final stage of the problem. Okay. What the problem says here? Okay. Uh, Now the problem became that the d minus c is positive to the power 1 by n, b minus a to the power 1 by n, and taking as n tends to infinity. As n tends to infinity. If we take n tends to infinity, we can take that n tends to, if we take n tends to infinity, so by sandwich lemma, this sequence will go to m. Okay. This sequence will go to m minus epsilon. Okay. And that should be less than equal. When we take the limit, that should be less than equal. And this becomes limit n tends to infinity n. Okay. And why this goes to n? Because we know, recall something from sequence that if a is positive real number, then limit n tends to infinity, it a to the power 1 by n is 1. How the actually this proof works is the proof of this sequential limit of a to the 1 by n is such that if we take a equal to 1, that sequence is trivially goes to 1. Okay. If a greater than 1, so a to the power 1 by n also greater than 1. So you can take a to the power 1 by n is 1 plus xn. And then a equal to 1 plus xn to the power whole to the power n, and just use the binomial expression 1 plus nxn. Okay, it is greater than nxn. So a greater than nxn. So from that you can consider that xn goes to 0. So a to the power 1 by n equal to 1 plus xn. Xn goes to 0. A to the power 1 by n is goes to 1. Okay. And the left case when a less than 1. So you take a less than 1 equal to a equal to 1 by b, where b greater than 1. And similarly this case. Okay. 1 goes to 1 and bn goes to 1. So a and a to the 1 by n goes to 1. Okay. This is the easy problem. Okay. You can get it from schema also. You can refer from schema also. Okay. I am just giving the proof already by verbally. Okay, verbally I am giving the proof. The if a greater than 0, so we take three cases where a equal to 1, a greater than 1, a less than 1. Okay. When a equal to 1, it is trivial. When a greater than 1, take it is a 1 plus xn, a to the 1 by n 1 plus xn, I use binomial expression, then you will show that it 1 by n equals to 1. And when a less than 1, you take 1 of them. Okay, clear. Now, by sandwich lemma, and this by sandwich lemma, by sandwich theorem for sequences, by sandwich theorem of sequences, this becomes a minus epsilon is equal to limit epsilon to n on 1 epsilon. And this holds for every epsilon. Every epsilon. This holds for every epsilon positive less than n. So from that it is clear that limit n tends to infinity, n is m. Okay. So we are proved that limit n exists, means it is convergent, and its limit should be supreme value of f of x. Okay. Clear? Yeah, we have done that problem. Okay, so this is our problem. And let me tell you one more thing, that this question asked in CMI 2019. This question asked in CMI 2019. Okay, question number something called 14. Number 14. And this question also asked in NBHM. NBHM 2024. Question number 17. Okay. Okay. In CMI exam, the interval is close interval 0, 1. Okay. And in the construction of n, it is in a to b modulus of f of x. In case it is modulus of f. Okay. So if you take f of x is any continuous function, and in between set x, that is g of x, and g of x modulus of f, then it will work. Okay. In CMI, if you open the question 14 in 2019, that will become in that question the interval is closed interval 0, 1. F is a continuous function and n is 0 to 1 modulus of f to the power whole to the power n dx whole to the power 1 upon n. Okay, then n is convergent, you have to prove. Okay, that is the question. And in NBHM 2024 17 number question, it is mentioned that an is constructed as a subsequence of this sequence. Okay, in that case, f is any continuous function, and they have not mentioned that is non-negative, but there is a term a to b f of s to the power 4 to the power n dx and whole to the power 1 by 4n. So similar proof will work. So I am not considering that, but I'm just giving the underlying idea how the things works. And if you know this question how to deal with, then you'll see that this question may be asked in later your interview batches or in any subjective exam. For subjective exam, this question is very good problem. Okay. Yeah. So we have done this problem, and don't hesitate to comment and let us know. How do you feel that? Enjoy. Okay. Okay.